Cloud, here we go. Excellent. All right. All right, so what was the conclusion? Yes, somebody suggested that we don't really have pairing here, right? Because you could have two numbers or three numbers, or actually a whole bunch of the same number given different rooms. My suggestion was that since we know Q to be already at least as large as n, right? Because I mean, Q contains a copy of n. So this set contains that one. So the cardinality, the number of elements, is at least going to be as large here as that one there. But what this does is it gives a pairing. Every number in Q is given at least one room, possibly more, right? Here the number 2 is given one room in this form, and then another room in this form, and another room in that form. So what this pairing actually implies is that the cardinality of Q is less than or equal to the cardinality of the natural numbers. So we have both inequalities, and consequently, they have to be equal. So even though it's not a real pairing in the sense that one element is paired with one and only one element of the other set, it suits our purposes here. And finally, right, I mean, we might have been tempted to believe that since you have infinitely many rooms, you can fit anything in. But we saw that the collection of buses with all different seating arrangements, the bus drivers themselves, only the bus drivers, not anybody else sitting in the bus. If we try to give just the bus drivers a room, we ran out of rooms. There weren't enough rooms to accommodate even the bus drivers. And we did that by assuming there was a pairing and showing that we missed a bus. There was a bus that wasn't attributed a room. We're going to redo that in the context of numbers. We're going to show that the real numbers are not countable. We're going to show that the real numbers are not countable, that there's not a pairing between the real numbers and the natural numbers. In fact, we're going to take a much smaller set than R. We're actually going to look at the set 0, 1. Right, the interval 0, 1. All the numbers between 0 and 1. I claim that that set is not countable. In fact, we're not even going to take that big of a set. We're going to take a subset of 0, 1, where A is the set of numbers between between 0 and 1 whose decimal expansion is made up of only zeros and ones. Example. Second example. Somebody give me a number in the set A. Zero point 111000010. This is an element of A. It's a number where the only numbers after the decimal are made up of zeros and ones. Right. 0 0 1 1 1 1 1 0 1 1 1 1 1. This is an element of A. Exactly. Well, Mr. Hussein is suggesting 0.4, but 0.4 is not made up of only zeros and ones, right? So we want to stay away from that. But as Christian suggests, 0.101101, this is an element of A. And so on and so on.
什么意儿咋又想到这个了？
Sorry, what was that? So what I'm suggesting, here's the claim. There is no pairing between the natural numbers and A, or between A and then the natural numbers. And how are we going to prove that? We're going to prove that by the same trick we used last time with the buses, right? What did we do? We assumed that there was a pairing, and then we constructed a bus which didn't have a room associated to it. Same thing here. We're going to assume there is a pairing, and we're going to construct a number in A that isn't attributed to any of the natural numbers. So suppose there is a pairing. Suppose we have a pairing. Then there's a number associated to 1. And there's a number associated to 2. And there's a number associated to 3. Which number is associated to 1? Which number of A is associated to 1? Right? I mean, let's say it was Christian's number here. And then there's a number associated to 2. Maybe it's 0.11100. And then there's a number associated to 3. And there's a number associated to 4. And so on and so on, right? I mean, regardless of what they are, there's some sort of association. There's a pair. We're going to construct a number very much like we constructed a bus, which isn't any one of these, what are we going to do? All the numbers have the form 0 point something, and the digits are zeros or ones. So in the associated to the first number, we're going to look at the first digits, and we're going to do the opposite. Here, you've got a 1 in the first digit. We're going to construct a number whose first digit is the opposite of 1, namely 0. So the number that I have is certainly not the first one, because they differ in the first digits. Associated to the element 2, to the number 2, is this one. I'm going to look at the second digit. The second digit here is a 1. I'm going to do the opposite. So it's not the first number, and it's not the second. And for the third, I'm going to look at the third digit, and I'm going to do the opposite. So this number is not the first, it's not the second, it's not the third. Associated to the fourth number, to number 4, I'm going to look at the fourth digit. And I'm going to do the opposite. And so on and so on. So this number is not the first number, it's not the second, it's not the third, it's not the fourth, and it's none of the numbers that are paired up with the natural numbers. So in the same way that you were missing a bus, you're missing this number. How are we doing? Questions? So we've displayed a number which is not paired. So this number doesn't have a pair, exactly that, right? This number is not paired with any of the numbers in the natural numbers. So the assumption we made must have been false. And the only assumption we made was that there was a pairing. There's no pairing. There's no pairing between A and the natural numbers. So this A is uncountable. It is uncountable. And of course, this bigger set is uncountable as well, and this bigger one is uncountable as well. So what have we said? Let's put everything together. We have suggested that the cardinality of the natural numbers is the same as the cardinality of the whole numbers, which is the same as the cardinality of the integers, which is the same as the cardinality of the rationals. These are all countable sets. But that is strictly smaller than the cardinality of A. This set A here, made up of decimal points whose decimal digits are only zeros and ones. It turns out that this has the same cardinality as the interval 0, 1, which actually has the same cardinality as the reals. You could use this method of proof for other sets of numbers, but not these sets. Not these sets, because in fact we gave a pairing which does work, where no element is left behind. right? So all of these sets are countable, and these ones are uncountable. These ones have more elements, even though all of them have infinitely many elements anyways, right? But this infinity is strictly smaller than this infinity. And now here's an interesting question. Is there a set where the cardinality of the natural numbers, which is the same as the cardinality of all of these, is smaller than the cardinality of B, but in other words, can you squeeze something in between these two? Can you squeeze a set whose cardinality is between the countable and the uncountable of R? The answer will surprise you. We'll discuss that next week. Questions in the meantime? So thank you all for coming, and sorry about this internet business. Not sure what's happening. Hopefully it'll be fixed by next week. Exactly that, right? Uncountable here means a bigger infinity than n. There are actually different sizes to uncountable. So here, let's just say the cardinality of the real numbers. All right. So you guys have a good weekend. We'll pick this up again on Monday. See you then.